I assume you've heard of supersonic, Christian?
Yes, I have.
What does that mean?
It's so fast that it's faster than the speed of sound.
Right, faster than the speed of sound.
Right.
And have you heard of ultrasonics?
Never.
Well, ultrasonics is sound that is of such a high frequency that you can't hear it. Our ears are, are only sensitive to a certain range, but you can make sounds that are higher than that. And that's what we're going to use to solve a problem. Here's a charcoal pencil, and that's a piece of frosted glass. Make a lot of marks on there.
Okay.
Get it all messed up. Okay. Now I'm going to cover that with another piece of glass.
Okay.
And hold the two of them together with rubber bands. And here's your problem. Clean off those marks.
I don't think I can.
Why not?
Well, it's too short of a space between this glass and this glass that I can't get in there
You
and
can't get in there and do anything with it.
rub it off.
Okay. Well, take the two pieces of glass and bring them around over here to this tank. And see that knob down there?
Yeah.
You turn it to the left, and that'll turn it on. You'll hear buzzing. Now slowly lower the sheet down like this so that you can see what's happening.
Okay.
You can set it down there there's a little tray in there. And there's liquid inside. See? So the liquid is starting up. Now watch.
Look at that. It's just going in between the little space there is. Looks like it's excellent. How does it do that?
Well, down below is a crystal. And the electricity is coming up here, and the engineers have designed it so it vibrates that crystal at very high frequency, much too high for us to hear. That sound that we're hearing, that buzzing, is not the sound. There's a high frequency, very ultrasonic sound. Ultrasonic sound, okay. And that's making the water vibrate and breaking and creating those tiny bubbles. But the minute the frequency reverses, the bubble collapses. Then when it goes the other way, the bubble is created. So back and forth, you have millions of tiny little bubbles. Well, it's called cavitation. You know what cavity is? A hole. So the thousands of little holes are being created all over in the water, and that breaking is doing the vibrating, and there's soap and water. And between the three of them, the soap, water, and the cavitation, you're able to clean all kinds of tiny little surfaces.
Wow.
You want to turn it off now?
Sure.
So scientists use this to clean all kinds of laboratory equipment. Jewelers could use it to clean rings and things where it would be hard to get in, side of things. And so it's very, very useful and called ultrasonics. Now, would you fill that glass with water, please?
Okay.
So we'll take a look at the action of those bubbles. And what I want to do is to play one glass inside the other. Make sure you have enough. Yeah, that's okay. Now here are little tiny beads. You want to sprinkle some on the surface?
Sure.
Okay, now sprinkle some of these. Okay, now turn on the ultrasonic cleaner.
Look at them, they're moving.
Yeah, you see how they're jumping all around because of those little tiny invisible bubbles? Here's a good group right there, huh?
Yeah, look at it. Looks like it's alive.
Yeah.
Little cells.
Yeah. If you turn off the machine, watch. Well, that gives you an indication, at least, of the kind of agitation that's going on inside the liquid. Would you hold that glass for a minute?
Sure.
Here is old club soda that I've had opened, and it's warm at room temperature. And I'll fill the glass with it. You can see not too much bubbling.
No.
What are those bubbles, you know? Okay, now you can let go, because I think they sit there. What are those bubbles?
The gas.
Yeah, carbon dioxide gas dissolved in the liquid. And you know what happens when you shake it?
Yeah, all the gas
comes out of solution.
Yeah, it
gets pushed out. Well, now imagine millions of tiny bubbles in the liquid that the glass is sitting in. They're going to hit the side of the glass, and they'll send vibrations into the liquid itself,
And then that'll make it.
And that'll make the gas
bubbles.
come up. Turn on the machine once, you'll see it. So this is called degassing, and scientists would use it this. If they have a solution and they want to make sure there's no gas dissolved in it, they could put it in here and out would come all the bubbles.
Would it ever stop?
Yeah, as soon as you get rid of all the gas. Might take a while, and we don't want to wait that long because I've got another thing. Turn it off. Back in the refrigerator, I have a very large bottle of root beer.
Okay.
And can you imagine what we might do with it in this?
Oh, no.
Okay, would you go get it, please, and bring it over to the sink? You have a good idea why I want to do this over the sink? Okay. This is full to the very brim, so we're going to vibrate all the root beer in there as fast as we can. So what'll happen when we take off the top and turn on the machine?
It'll just go.
Now, why? Wait, first of all, why?
The
Crystal?
crystal inside the machine will vibrate. Then it'll
This liquid.
Yeah.
Right.
Vibrate the liquid.
And
then that will shake the.
Will create little tiny bubbles, remember?
Right.
It's called cavitation.
And then that will kind of shake the glass a little bit, which will shake the root beer a little bit, which will make the
Root beer.
go up.
Okay. I'll turn on the machine, and I think you're safe if you stand about
okay.
right there. Are you ready?
I think so.
Here we go.
Oh my God.
Root beer, you've heard of a fountain treat?
Yes.
There it is. Root beer exploded sort of because of ultrasonics. You've seen manhole covers on the street many times. They're usually round. Why? Here are two models of manholes. One is square and the other round. Both have covers which are removed so workers can go below the street level to work. If by accident the square cover were moved over the hole, it could line up along the longer dimension, the diagonal, fall in, and possibly hurt the workers below. The round cover and the matching hole have no longer dimension because the diameter of a circle is the same length in all directions. Therefore, it can't possibly fall in. And that's why manhole covers are round. I don't know if you've ever done this famous experiment, Lila, but here's a candle, and I have a bolt at the other end so you make it nice and heavy so it'll sit here in a dish of water. And here is a jar with a big sort of mouth on it that I can put over the top of that, so it'll end up with the candle inside. What'll happen?
The candle will go out.
Why?
Because it'll use up the oxygen that's in there.
So go ahead, put the bottle over there real quickly. Just put it right down over the top. That's it. Okay. Now let's see if you're right. You say the candle should go out?
Yeah.
There it is, getting weaker and weaker.
It's going down.
Finally goes out.
There, it's out.
But look what's happening down below.
All the water's coming in.
Well, at least some of the water's coming in. It's about up to here, right?
Yeah.
Why?
Maybe to take the place of the oxygen that was burned?
Well, that's sort of the explanation that most people have used to explain this phenomena when they've done this many, many times. In other words, the oxygen was consumed in the candle flame, taken from the air inside, so the outside air pressure pushed the water up to take the place of the oxygen that was used.
Yeah.
Wrong.
What?
Wrong.
How come?
Well, let's do this another way and see if you can figure out why that's wrong. See this other candle over here?
Yeah.
And you see what's next to the wick?
It's a little coil.
Okay, turn that knob all the way up, and that coil will get hot because we're going to run electricity through it. And as soon as the candle is lit, well, you can turn it out. Okay, now turn it out. Whoop, there we go. So the point is we can light the candle without a match.
Yeah.
After it's in the bottle. Like that. Now we can light the candle, right?
Right.
But before we do that, let's take out some of the air. You take that end. Now I'm going to put this end in the bottle. and then you suck out some of the air so that we can make the water rise inside the bottle. Okay, go ahead. Okay, now stop right there. Okay.
Tastes smoky.
Tastes smoky? You're all right, though?
Yeah.
Okay. There we are. The water level is, well, as you see, what, 2-3 centimeters up?
Yeah.
All right. Now all you have to do is turn on the current, and we can light the candle, and the same thing should happen. It should go out, right?
Yeah.
All right. Let's see if you're... Okay, now turn that out. Now watch.
It's not rising.
No. It's not going out quite yet either. Wait.
There, it's out now.
How's that water level compared to what it was before?
It's not, it hasn't changed.
It hasn't changed. So your explanation about the water went up because it used up some of the oxygen in the air must be incorrect, right?
Right.
Well, when scientists have done this very carefully and analyzed the products of the combustion, they found that the carbon dioxide and other products given off from the flame take about the same space as the oxygen did before the flame. So the water shouldn't come in at all. Yet it went up over there.
Oh.
All right, let's do that one again now. See if you can see what it is, the real explanation for it. But before we do that, I have to fill that with water. Why?
To push out the rest of the carbon dioxide and stuff?
We want to make sure we have a bottle of nice, fresh, clean air. And one way to do that is to fill the bottle with water to force out all the old air. And now what are we filling the bottle with?
Air.
Right, air.
Oxygen.
All right. Okay?
Yeah. Oh, there, finally.
Okay. Now this time, Lila, when you turn it over and put it down quickly, watch very closely what happens right at the level of the water.
Okay.
You didn't pay attention to that last time.
No.
Okay, watch what happens now.
It bubbled.
Okay. So what difference is that going to make in the experiment?
Well, some of the air came out.
Mm-hmm. The candle is obviously heating up the air inside.
Yeah.
That makes it expand, right?
Right.
That's what the bubbling was. The hot air coming out. What happens when the candle goes out?
The air contracts.
Yes.
And the water fills up the space.
Outside air
when the
pressure.
water came out.
Right. So it only takes up the space of the air that you heated up and let escape. And there it is. Well, just about where it was before.
Oh, now I get it.
Okay.
I was wrong before.
Yeah, well, and you had a lot of company. A lot of people were wrong with this experiment because it's not because you use up the oxygen, but because you heat up the air, and that makes it expand. Hi, Karen.
Hi, Mr. Wizard.
Hey, that's a neat new bike you got there.
Oh, thanks.
When'd you get it?
I got it in March.
Oh, nice present from somebody, I assume.
Not really a present. I had to pay half of it.
Oh, well, congratulations. Very nice. I see it's a 10-speed.
Yeah, it is.
What gear were you in?
I was riding in 5th.
You know what that means, 5th gear?
No?
Well, let's come on over to my workshop and let's have some fun investigating various kinds of gears.
Okay.
Okay, now these are the gears that are sort of on your bicycle. This big one represents the gears that are by the pedal.
Okay.
And you have two big ones like this, don't you?
Yeah.
Then this one represents the gears that are on the back wheel, and you have 5.
Yeah.
5 times 2, 10, 10 speed. Okay. Now turn this wheel once by watching that mark, and then count the number of times this one goes around.
Okay. 1. Goes around twice.
Twice, right. Now these numbers here represent the number of teeth. This one has 30, that one has 15.
Oh.
So now I have a very difficult mathematical problem for you. I'd like you to divide 30 by 15. So would you write it up here?
Okay.
Equals what?
2.
Right. And notice that that's what happened when you went around here. This went around twice. So you can figure out the gear ratio by simply counting the number of times one wheel goes around and checking the number of times the other wheel goes around.
Oh, okay.
Now, if you had this set up on your bicycle, would you go faster or slower? than if these were both the same size?
It'll go faster.
Faster. In other words, it'll go around twice, right? For every
Yeah.
pump of the pedal. Okay. That was a simple one. Now comes a little more difficult one, because you change gears, don't you?
Yeah.
On the bike, okay? So we're changing gears too. Here's the 0 mark. And here is another gear. There's the 0 mark. Now, count the number of times this one goes around while I turn that one once.
1. And
Something.
yeah, about 3 and a half.
You know how to find what we did before?
Yeah.
We divided 30 by 15. Now what do we have to divide by?
Divide 30 by 22.
Okay, at least write down the formula. Go ahead.
Okay.
Okay, now to make it easy, here's a calculator.
Oh,
You know how to use it, all right?
Yeah.
Okay. 30 divided by 22 equals. What is it?
I think I have the wrong answer.
Why? What does it say?
1.3636. No. Yeah. 3636.
Why is that the wrong answer?
363. I don't know. It
Yeah,
looks
don't
a
you
bit
believe the
big.
calculator?
I guess.
Write it down. Let's 1.36. Yeah, over here.
Oh, okay.
0.36. And if we had more paper, you could keep going. That's enough. That's enough. That's enough. That's enough.
Last number,
1.36 is good enough. Now, let's start and do this one again, and you watch. You see whether your answer is correct or not. Get the 2 zeros together. Okay, you ready? I'm going to turn this once. You count this. Watch. There's what? 1.
Yeah, 3 and a 6.
1.36, right?
Yeah.
Okay, so that means that if you change the gears on the back end of your bicycle, in the rear wheel, and you put this gear instead of the other one, would you go faster or slower?
You'd go slower.
Slower, and you'd have more power.
Yeah.
So that's why you change the gears on the back end of your bicycle, to change the speed with which the back wheel goes around.
Oh, I didn't know that.
Okay, well now let's go out and try it with an actual bicycle. We'll do the same sort of thing. Okay, Karen, I think we've got it set on one of the nice gears there, and we've got the wheel divided up into 10 equal parts, right?
Yeah.
So I'm going to go around once with the pedal. I'll start the pedal right there opposite that red strut. You move the back wheel so that you get 0 right opposite the chain.
Okay. There we are.
Okay? I'm going to go around once with the pedal now. You count the number of times the wheel goes around. Here we go.
0.1 and 0.2, 0.3, 0.4, 0.5, 0.6. There's 0.7, 0.8, 0.9, and 1. Then there's 0.1 again, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 2. And then there's 0.1, 0.2, 0.3, 0.4, 0.4, no, 2.44.
2.44.
Yeah.
Okay. Now let's change gear ratios. Go to this one.
Okay.
Do the same thing. You ready?
Yeah.
Okay, I've got mine set. No, you can't go backwards like that.
No.
You've got to go all the way around. Okay, here we go.
Okay. 0.1 and 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. There's 1 rotation. 0.1, 0.2, 0.3, 0.4, almost 0.5.
1.49. Okay,
Yeah.
so this is the back wheel's going around slower this time, right?
Yeah.
Okay. Why would you want to change gears like that now?
Well, so you can get either more power or more speed.
Right, one or the other. And in a 10-speed bike, you have 10 choices.
Yeah.
And if you wanted to, you could check out the gear ratio of all 10 speeds. Stacy, see there's a cup suspended above the counter on the point of 4 steak knives.
It looks impossible.
And you know, of course, it's not, because you know I
Right.
set it all up. Well, the secret is in this cup right here.
I don't understand.
Well, first of all, let me remove it, and you'll see that the secret, first of all, is under it.
Oh, I see. They're all overlap.
Yes, and you've done that with cardboard carton tops, haven't you?
Yes.
And the reason why I said that 5th cup is the secret is you can use it to support the knives when you set it up. Go ahead, set it up.
All right. That one there.
Okay, now, there you go. And that one goes on top of that one, right? Okay. Now lift this knife. So you no longer need that one.
Right.
Pull it out, put it on top, and you've done it.
Okay.
Congratulations.
Thank you.
The tide has gone out in this South Carolina inlet, so the men can expect the oyster beds and mark them with saplings. Once, the oysters were harvested by hand, but these men will harvest the oysters in a new way with a machine designed and built by Dr. John Collier and his fellow researchers at Clemson University. The experimental harvester was constructed on the hull of an old flat-bottom houseboat. The tide has come in, and the oysters are now several feet underwater, their position marked by the saplings. When they reach the bed, this part of the machine will be lowered into the water. The flexible steel teeth will break off the top layer of oysters. The other belt moves in the opposite direction, scooping the oysters out of the water onto a conveyor belt that piles them onto a barge being towed alongside the harvester. The machine must be carefully adjusted to harvest only the top layer of oysters without harming the layer below. The experimental model can do the work of 8 human oyster pickers, but few people are willing to do the hard manual labor of picking oysters by hand, so the machine is doing a job people don't want to do. The oysters are now ready to go to a factory to put into cans, but Dr. Collier and his crew are not headed for a factory. They're going to demonstrate a solution to the second problem the harvester was designed to solve. You see, many oyster beds have been closed because the water in which they live has become polluted. The crew are taking these oysters to cleaner waters. Getting the oysters back into the water is relatively easy. Just shove them off the barge with a stream of water from a hose. The oysters will attach themselves to the bottom to form a new bed. Laboratory tests have shown that after only 2 weeks in clean water, the oysters will be safe and ready to eat. Cans of oysters may again become plentiful thanks to the invention of a mechanical oyster harvester. Darren, here's a simple little challenge for you.
Okay.
Put the balloon in here like that, and I want you to blow it up and fill up the whole bottle with the balloon.
All right. It didn't fill up.
No, you got a big space down there. Why? Why can't you do that?
Well, maybe there's not enough air going out.
Going out?
Yeah.
What do you mean going out? Where's
Well,
the air going out?
There should be air going out of the bottle,
Right.
so there's room for the balloon to go in.
Right, and you're closing it off here by squeezing the balloon up here like this. Okay, so let the air out. Now, in other words, in order to blow up the balloon so it fills up the bottle, you got to get rid of some of the air down here. Drill a hole in the side of the bottle, for example.
Yeah.
That would be one way.
Yeah.
May I make a suggestion?
Oh, okay, so you put the straw in, and then there's enough air going out.
Okay, try it.
Okay.
Okay, pinch it off right there. Now, hold it, and now let's pull out the straw. And you could now challenge your friends to, boy, you really blew it up tight. I gotta get the straw. Now we could tie the balloon off up here like that, and you could have that sitting in your room. And you can now challenge your friends to try to blow up the balloon like that, and they won't be able to do it.
Okay.
Until you give them a little clue, a soda straw.